We continue our study of quantum machine learning. In the last video, we started discussing quantum variational circuits. From quantum variational circuits, we can make many different kind of machine learning algorithms. In this video, we start with how to train quantum variational circuits. For training, we'll have a data x1, y1 to xm, ym. As usual, xi's are the observations, yi are the labels corresponding to it. And we fix a variational circuit. Variational circuit has a parameter theta. And that theta parameter needs to be found such that it minimizes the empirical risk. That is 1 by m, sigma is equal to 1 to m, L f theta xi yi, which we are going to denote as c theta, and L is the loss function. For example, for classification, L is given like this. L f theta xi yi is equal to 1. If f theta xi is not equal to y, it's equal to 0 otherwise. So it's basically this quantity counts the average number of errors for a given theta. To find the optimal parameter theta, the algorithms which are most common are iterative gradient descent kind of algorithms. The simplest among them is called gradient descent, but the rest of them also have the feature that these are iterative algorithms, and at each step you need to compute the gradient of the cost function c theta. Then the gradient descent works as follows. You start with some random theta 0, and then theta k plus 1 is equal to theta k minus eta gradient theta c theta. Using chain rule, delta c theta by delta theta is equal to delta c theta by delta f theta into delta f theta by delta theta. If we make L to be differentiable, the L example given above is not differentiable, at least at one point. Actually, but you can make variations so that these you can get approximately functions which are differentiable. Then C delta C theta by delta f theta is easy to compute. And what we are left with is delta f theta by delta theta. This is what we talk about in the next few slides. And you will find that in our scenario, this does turn out to be a challenging thing. Remember, in our variational circuit case, f theta x is the expected value of the quantum circuit output. And this expected value is computed by taking average over multiple measurements of the quantum circuit. So therefore, this f theta x that we get is an expectation. It has errors. And if we take delta f theta by delta theta approximately to be equal to f theta plus delta minus f theta by delta, where delta is small, this is the usual approximation for gradients we take in this setup, because at each f theta, there will be estimation errors. Computing these quantities for delta small can lead to large errors. So we look for other possibilities. Another possibility is f theta is this quantity. 0, w star theta, m, w theta, 0. 0 is the input vector. M is the operator with respect to which we are taking the measurements. And w theta is right now representing the overall quantum circuit at theta. So then to take the gradient, since inner product is linear, you can take the gradient inside, and this becomes inner product with respect delta by delta theta, w star theta, you have a gradient here, and then you have a gradient here. So you can think of considering each one of them as quantum circuits, and then they take the expected values with respect to the circuits given on these sides. However, the issue now is that even though w theta we started with is going to be unitary operator, for quantum circuit it has to be unitary operator, its gradient may not be unitary. If that happens, then we will not be able to use this because this will not be unitary and this will not be unitary, and we will not be able to construct them via quantum circuits. Now we consider another possibility. F theta, we again write it as 0, C star theta, M G theta 0. Now instead of W, we have written here G, and you will see the reasons here. Now this can be written as this whole quantity here, we are writing as K theta. Then taking gradient of F theta with respect to theta, we can take the gradient inside and 0 delta by delta theta, K theta 0. If this J theta is e raised to a minus theta G, so this will be a simple scenario, but the more general scenarios will happen in the same way. This is just to illustrate it in a convenient way. If G theta is raised to minus I theta G, and we saw many examples in the last video when these circuits are designed in this way, then we can show that G square theta is equal to I, and in that case, G theta, this quantity can be written as G theta is equal to cos theta I minus I theta sine theta G. And taking this G, then this K theta can be written as A plus B cos theta plus C sine theta. Now, taking derivative of K theta, we realize that it has components cos theta and sine theta. D by d theta cos theta is minus sine theta, can be written as cos theta plus pi by 2. D by d theta sine theta can be written as sine theta plus pi by 2. So therefore, d by d theta k theta, I have written here d by this d, but we could replace it by the other gradient partial derivative in this case. And this can be written as k theta plus pi by 2 minus k theta minus pi by 2 by 2. In the general form, uh, you know, instead of writing this derivative cos theta plus pi by 2, you can in fact show that this more generally can be written as delta by delta f theta by the delta theta f theta plus s minus f theta minus s divided by 2 sine s. This becomes a special case in that case. And here s is not equal to 0, otherwise the denominator is going to become 0. So we can write it, this gradient of f with respect to theta in this form. Now, to compute the gradient, we compute f theta plus s and f theta minus s from the circuit measurements corresponding to theta plus y and theta minus s, where this s that we are taking will not take it too small. Because if you take it too small, then we'll again get into the trouble of large errors. Here we have the choice of not taking it small. And that way, then from this expression, computing each one of them, we can get this derivative. We can extend this kind of argument for more complex g theta and also for taking second derivatives. Del square theta f theta. In case instead of gradient descent, we are using Newton type optimization algorithms. So that way those problems can also be solved. So finally, we are back to, in the case of gradient descent, theta k plus 1 is equal to theta k minus theta delta f theta at theta k. This is going to be computed as above eta is some small positive constant. In this algorithm, if this quantity here becomes small, then the convergence does become slow. There are more issues with these training algorithms. This above issue that we talked about, where the gradient is small, is known as vanishing gradient problem, and convergence is slow. It can occur in deep or highly expressive variational circuits. We talked about all kinds of variational circuits, and when their parameters are large, they can become very expressive, and we may want some time expressive so that f theta represents a large class of functions in a good way. The vector space can be very high, and these circuits, quantum circuits that we have may have outputs which can be highly entangled. Because of all these reasons, we can get into vanishing gradient problem and other optimization issues can arise. So these are the problems that one faces in training variational quantum circuits. Now we'll use variational quantum circuits for autoencoder decoder circuits that are very popular in neural networks. The above variational circuits that we have talked about, we can think of them as neural networks in the usual machine learning setup. And then we will use this variational circuits, quantum circuits, to make an autoencoder decoder uh, network as well. So in this autoencoder decoder, the goal is we use neural networks to compress data. We have talked about compression of data via PCA in the last video. Now we are talking about the same problem, but instead of using calculating the uh, eigenvectors and so on of the dominant eigenvalues, we use just the neural networks in this case, and it works as follows. X is the input with dimension D. D can be large, and we want to compress it into smaller dimensional Z with dimension D prime, where D prime is much less than D. And we have already explained the reasons why we want to compress. And we want to, of course, compress in such a way that most of the information, the useful information in X is still retained in Z. So this is done such that taking this Z, we can define a decoder to reconstruct X hat such that norm of X minus X hat is minimized. So we will have an encoder, which will be made through the neural networks. We have a decoder, which will again be made by the neural networks. And they are made in such a way so that these things are minimized. So this is how autoencoder and decoder works in the usual deep learning machine learning algorithms. Now we talk about the quantum versions of this. In quantum versions, we will be discussing the same way. X is the input. You pass through the encoder, you get the Z. Then you pass through decoder, you get X hat. You have training data. This is, we should be writing just X1 and XM. And we want weights W in the encoder and decoder in such a way so that for this M data sequence 1 by M, sigma is equal to 1 to M, norm of Xi minus Xi hat squares are minimized. So this represents the autoencoder decoder setup in the classical way also, as well as you will see in the quantum case. So quantum case, we will consider a state with n plus k qubits. Input state is n plus k qubits. This is a large dimensional thing. We want to compress it and into a n qubit states, right? From n plus k qubit to n qubit state, we want to compress this, and we want to do in such a way that from the states, n qubit states, we can recover the original state whenever we want. So we have training sequence of phi I is equal to 1 to m, n plus k qubit states, which we are going to write it phi I A B. A and B are two registers. A is of n qubit size and B of k qubit size. So this is the state of n plus k qubit input, and we want to compress it to n qubit states. So the circuit for this is the input, n plus k qubit input. You pass it through a variational quantum circuit, which we are going to write at UW. W is the parameter. And at the output of it, this again is this overall thing is n plus k. This part, the initial n part, we are writing it as phi ia, corresponding to psi ia. And here we put a swap gate. And there is another input here. So this is the input that you want to compress. You put another input of size k. This could be just all zero vectors. So you could take all zero vectors or some very specific thing. So for us, maybe we can just take it all zero vectors of k qubits. Here we have the swap gate. So which means that whatever the state here is comes here, and whatever here it was all zero comes here. So if you look at the state, quantum state here, this is n qubit phi I state, and this is k qubit zero state. And you feed this to adjoint of u, w. And here, whatever you get, you call is rho w out I, corresponding to these I. And we have m states. So for each of these i's, n plus k states, we'll have n qubit states, and at the output using this circuit from this, basically, we are going to get n plus k qubit state, and we would like it, this circuit's UW in such a way, this output is as close to the input as we could possibly get for this n and k. So what we can represent it as a problem of obtain W, this W parameters that minimizes minus of F psi IAB, the corresponding output rho IW, and F is a fidelity measure. F measures the similarity between this state and this state. And so we would like W so that this output that you get is as close, its fidelity is as close to the input as possible. And we are taking summation over all I. So find W that will, so we put a minus here. This we wanted to maximize. By putting minus here, we minimize this quantity. Find W that this is minimized. And this is how we can get the quantum encoder decoder from variational circuits. Now we use kernel methods for variational circuits to get optimized algorithms which are simpler to optimize. All through we have been seeing in the variational circuits, we have a parameter theta, which and the output of the circuit is f theta, which could provide us classifier or a regressor, and we want theta, which will give minimum errors, right? So we are trying to optimize parameter theta. And we have our given the algorithms, gradient descent kind of algorithms, which can provide this optimal theta. What we are looking at now is use kernel methods to solve this optimization problems of getting optimal theta in a simpler way. So how it is as follows. Training data, xi, yi, I is equal to 1 to m, x belongs to rd. Circuit, that variational circuit that we are going to have, 0 is the input state with whatever dimension, passes through a quantum circuit Sx. X is the input, these inputs, so Sx, and the output of that is represented as phi x. Then it goes through the variational part of the quantum circuit, W theta. Theta is the parameter theta that you want to minimize. The output of that is a state which will take measurement with respect to the operator M. So therefore, F theta x, which is the mean of the outputs here, as we have seen earlier, can be written as norm of F, inner product of Fx, W star theta M, W theta phi x. This is the phi x. And of course, we want theta that minimizes this cost function where L is an appropriate cost function, which tells the difference between the output corresponding to Xi from the theta circuit and the actual level Yi of the training data. We define M theta prime as W star theta M W theta. That was the quantity which was inside. And we can show that F theta X that we have given here can be written as trace of M theta prime rho X, where rho X is phi X tensor conjugate gradient phi X. We can show that this quantity Kxx prime defined as the trace of rho X prime. So rho X and similarly rho X prime here. This K defined here can be shown to be a symmetric positive semi-definite kernel. This is how we can now use the kernel theory that we have been using before. Now the optimization that we have talked about here, finding the optimal theta in the variational circuit via this kernel framework can be shown to be equivalent to the following problem. The problem one that we are talking about in general is a non-convex optimization problem. So therefore, optimization this theta can be a serious concern, and writing it in this form, and that is 1 by m sigma I is equal to 1 to m, L is the same L given there, J is equal to 1 to m, gamma j, K, xj, xi, yj, where L is the function that we have given earlier, loss function. If L is a convex loss function, this problem becomes a finite dimensional convex optimization problem. So notice that this is a minimization problem where we have to find parameters gamma 1 to gamma m. This is m number of this variables that we have to find, which is equal to the number of training sequence. And if L is convex, we are trying to optimize here a convex, finite dimensional convex optimization problem. And this is one of the simplest problems. And using gradient descent, stochastic gradient descent, and other methods, we can get the globally optimal solution for this. If we represent that optimal solution by gamma 1 star, gamma m star, then the optimal classifier or regressor that we have been talking about can be written as f star x for any input x, sigma I is equal to 1 to m, gamma j star k xj x. X is what we are computing at it, and xj's are the training sequence. So what we have shown is using the kernel methods, the non-convex optimization problem of variational quantum circuits can be simply converted to a fine dimensional convex optimization problem. And we have seen that variational circuits can represent different kind of circuits in classical algorithms, and hence a very large class of useful machine learning algorithms can be converted via this, and we can get the optimal solutions in a very efficient way. Thank you very much.